Hello, my name is Brendyn. I will be conducting this presentation of this project for my group members, Benjamin, Jacob, and Abdul. We tried to do it in class, but it was too loud and we couldn't get recording processes to work, so I'm doing it at home for my team members. Starting off with the project, we're trying to design an electric vehicle controller for to control the speed. The customers, as we will go into the next slide, I've stated some specifications that we need to meet in order for them to design their vehicle. It needs to be at a steady state speed of 12 radians per second with a minimum overshoot less than 2%. There needs to be a comfortable acceleration that is greater than zero point 0.1 seconds. There needs to be a low jerk from the voltage readings, and there needs to be a quick response time less than 2.2 seconds. The motor voltage needs to stay under 24 volts. And these are just some minor specifications to the designing of the controller. Uh, our objectives are to identify the motor and the circuitry parameters, design a simple proportional controller, further design by using a PI and a PD controller, and finally design a complete PID controller. That's kind of what we went through and did throughout the projects. Here we go again, going through the lab processes that we went through with designing this controller. We start off by understanding the mechanical side of this type of project. We had a disk with a sensor that read the radians. We idealized that the sensor was accurate. Um, then we also went into the controllers or the Arduino board and the voltage and the voltage box and seeing how everything kind of connected and everything worked together before we actually started going in through controller design. Uh, we had to mathematically model and set up the wiring for the Arduino boards. So we did understand how this whole system worked before we went in and jumped in. We tested things as far as voltage to velocity, making our equations for our plant. And then we went in, once we found all that, and started making controllers. We made a proportional controller, PD controller, a PI controller, and then lastly a PID controller. We saw throughout each experiment the different capabilities of each controller and what it limited to us. So what we came throughout in the very last lab is that the PID controller is the best for this project, and you'll see why here in a second. We're idealizing that the motor is linear, the motor is ideal, both wet and dry friction are present in the system, and the components are used are brand new and are working correctly. So what we started off doing within this project, we used a CISO tool to theoretically find what are the best values for this PID controller to model it. Uh, as you can see on the right-hand side, the step response from R to Y, that is just what our response is to our input and output. So as you can see, it does reach a steady state value of 12 radians per second. We tried to keep it in with the parameters of a rise time of greater than 1 and a settling time of less than 0.2. As you can see, it's not quite perfect, but it is close enough for what we tried to design. For this kind of controller, there are multiple other types of controllers that could be used, as like, for example, a PI controller can be used. It just depends on how you set up your pre-filter and whatnot. But yeah, there are other designs that also work within these parameters. So going into it, using those parameters from CISO tool, we plotted it using it an actual real experiment, used it in the Arduino code and ran the wheel and saw what values we actually were, the theoretical values or the experimental values that were produced. As you can see in these first values, we had a large overshoot with a lot of oscillation. So what we ended up doing was first starting by decreasing the Ki value significantly. This is from the integral value from the Ki over S. As you can see, this produced a large undershoot that was very slowly coming up to the 12 radians per second that we wanted. So what we ended up doing was as you can see, we had 3.5, 1, and 2. What we ended up doing was just increasing the Ki again just a little bit, just to see what is the right value for us to use for Ki. As you can see, our undershoot was still a little low, but we actually ended up coming up to the line a lot quicker than previously, so we ended up staying up with that value. Now what we ended up doing was changing our KD value to zero point 0.5, which was we thought was going to increase the or reduce the undershoot and make it more on the line. What it ended up doing was actually doing that, but also increasing the oscillations. So what we did next was try and decrease KP, our proportional gain, and that sort of worked. It didn't really work too well. It made it oscillate a little more. So what we ended up doing was decreasing KD again to see if we could actually uh, get it to oscillate less, but we also increase KP to see if we get it up more to the line. As you can see, it did result in better. It did show better results as far as getting to that line. It was still oscillating quite a bit, and it still had some undershoot, but it was a lot better than what we previously had. So what we did next was increase KP again and increase KD just a little bit to see if we could tweak some things. We got a little bit better results. It was, as far as the undershoot was less, but the oscillations were a little greater. So now what we ended up doing was just going back to the old KD value and decreasing our KP. And what we ended up getting was actually a lot better as far as oscillations along the 12 radians per second desired output, but our overshoot and undershoot was still great. So what we ended up doing was decreasing our KP value, which increased our undershoot drastically. But what ended up happening was we do eventually get to the 12 radians per second, and actually a lot quicker than what we previously saw in our third attempt for the PID controller. So we ended up going with that application for the best designed overall controller for this situation to meet the outcomes that the company is applying to us. So how can this controller be used for other applications? You can see down here at the very bottom, we have examples that would be something for a controller like this, like a hydroelectric generator, modeling and pointing a system for an antenna array, and creating a controller for automotive uses. These are just a few examples to the endless amounts of systems that these kind of controllers can be applied to. It all depends on the specifications that are required and what is being transferred as far as from voltage to velocity or acceleration or radians per second, how the plant's designed, how the sensor is designed, and what is necessarily needed in the controller to meet outcomes as far as like steady state error equals 0, or is at a percentage less than or greater than something. These are all just specifications, but controllers can be designed around what we have been doing in our previous labs. So on that note, going to end this, and that is the rest of our presentation.